Okay, let's choose self-control here. All right. Hopefully folks can hear us okay.
Yeah, it's better.
Okay, better. Okay, I think it's because I moved.
Okay, so I want to start off by telling you what we thought we knew back in 2006, and then the rest of the talk will be bringing you up to date with the tremendous amount of progress since then, as well as a number of failures, rather spectacular times. So how does it all start off with people are looking for planets or thinking about it for many years, hundreds of years, but the key thing is that it's really difficult to just go out and take a picture of them directly. This is actually a figure from the TOPS report, a NASA report from 1993, showing you the light reflected by the Earth at visual wavelengths, as well as emitted, as well as infrared wavelength. And the problem with Earth is quite faint in reflected light. It's about a 30th magnitude object at 10 parsecs, which is not impossible to see. That's like no fainter than the Hubble ultra deep field type thing. You can see it with a couple of many orbits of Hubble orbits. The problem is it's right next to something which is 10 to the 10th times brighter right next to you. So it's all a problem of contrast. Things improve a bit if you go to mid infrared because they're interesting signatures out at that wavelength. But then, of course, you also have to have a telescope that's proportionally larger in size, or to beat the lambda over d Rayleigh criterion. So mid infrared would work, but you have to have a really big telescope to do that. So because this rather high difficulty that people realized from the very beginning of direct detection, a lot of the early work was simply looking for indirect detection, which starts off with the basic fact that we do not, planets do not orbit around the sun, they orbit around the center of mass of the system, same thing for the sun. So for the case of our solar system, if you're looking at our solar system from 10 parsecs, we would see the sun wobble back and forth over Jupiter's 12-year orbital period over an angle equal to about a milliarc second, which is actually the size of the sun's radius. Pretty small, it's like a dime at 1,000 miles. At a milliarc second, there was something that astronomers felt that they could measure to look for that wobble over a long period of time. So that's the first indirect method that historically came along. That brings us along to Barnard's star, which was discovered in 1916 by Edward Emerson Barnard. He was an amateur who really liked to find comets, and one day he accidentally found something really moving really fast across the sky. It turned out to be now named Barnard's star, is moving at 10 arc seconds per year, which is screaming. And if something's moving fast, it means it's in the sky. It means it's probably pretty close. Barnard's star is indeed close. It's the second closest system after the Alpha Centauri triple system. It's out at about 1.8 parsecs. So that's exactly what you want for an astrometric detection, looking for the wobble of that star due to any planets around it, because clearly the closer you are, the bigger the wobble is. The other great thing about Barnard's star is it's about 1/7 the mass of the sun. So again, its wobble will be 7 times larger than the sun's wobble would be. So Barnard's star is basically a perfect star to try to do astrometry on. In fact, actually, I think some of the folks from Barbara MacArthur from Texas used HST to try to do astrometry on Barnard's star, but didn't really find anything. Person who thought he would find something was actually Peter Van Camp. In 1937, he became the director of the Sproul Observatory at Swarthmore. In 1938, he began taking semi-annual images of Barnard's star. He had a series of undergraduates, including Nancy Grace Roman, who measured the plates for him by hand. And they had multiple students measure the plates to sort of average over their numbers to see what the value would be. And after taking data for 25 years, in 1963, he finally published his claim for evidence of a Jupiter-mass planet around Barnard's star. So here's RA and DEC, function time, and let's see if the cursor works. The excursion here is plus or minus a micron, which is about 10 milliarc seconds. These open points here are the same as these points over here, because assuming he's got a closed orbit. The bigger the point, the more you should believe it, and the smaller the point, the less you should believe it. But this wobble would be caused by a 1.6 Jupiter mass object in a 24-year period. 4.4 AU sounds pretty Jupiter-like. The only weird thing about it is it's not a pure sine, so it's not a circular orbit. It's somewhat eccentric, but that seemed to be not unreasonable. So this basically went into the textbooks. When I taught undergraduate astronomy in UC Santa Barbara in the 60s, we used George A. Bell's classic textbook that has Peter Van Camp's Jupiter mass planet in there. It was accepted to be, but it was thought to be not terribly interesting. We figured there, something interesting in galaxies. So that's where it was in 1963. But then along came George Gatewood and Heinrich Eichhorn. Gatewood was doing his PhD under Heinrich Eichhorn, sort of the dean of astrometry, and Eichhorn says, why don't you do something really interesting, which is go back and look at Barnard's star using data from a different telescope. So Gatewood processed the data from not the Sproul Observatory's 24-inch refractor, but from the Van Vleck Observatory's 24-inch refractor. And he measured the plates not with undergraduates, but by using the brand new plate measuring machine the U.S. Naval Observatory had made available to them. And after analyzing that data, here's the what they came for. You can see the this is just one coordinate on the sky, and the dashed line is what the prediction was for Van de Kamp's orbit. Again, there are points repeated here on both sides, assuming you've got a circular repeating orbit. Big points are believed to be believed, little points not so much. These maybe not so much, not so much. And this one here, you should not believe at all, because that's a fleck of dust that came along when I converted this talk from 35mm slides to PowerPoint. But Peter Van de Kamp would have liked that. He would have argued that helps support story. But anyway, a guy, Gatewood and Eichhorn, very gentlemanly way said we find no evidence for this planet. And that same year, 1973, another paper was published by one of Van de Kamp's colleagues, John Hershey, of another star, a Gliese star, which seemed to have the same wobble that Barnard's star did. So that means either they both have 1.6 Jupiter mass object on a 24-year period, or else something else is going on. And that's exactly what had happened. Let me go backwards. Sorry, there we go. Problem was that in 1949, oops, touching it too much here. Where's the okay, here we go. In 1949, there had been a change in the emulsions being used. And in 1957, they made a very major adjustment of the lens. So that's what made both of those stars appear to wobble. At that point, the idea of Barnard's star's planet began to disappear slowly from the textbooks. And about that time, eventually NASA got interested. In 1988, they formed the Planetary Systems Science Working Group, which I had no idea what the hell it was about. I was invited to join it, and I thought it was something about our planetary system. Turned out they meant extrasolar planetary systems, because we didn't know of any at that time except for Barnard's, which had just disappeared. They're making progress in the serious study, and that led to that TOPS report that I showed you the figure from earlier on. There'd also been, interestingly, a NASA complex committee on planetary and lunar exploration that I was involved in, which published a little appendix at the end saying why transit photometry would never work, which I thought was, given what we know now, which you'll see later on in the talk, turned out to be spectacularly wrong. But there's a published document saying this won't work, so forget about it. Along the way, we also suddenly had the Millark second pulsar come along, which was taken to be a threat to the field. Those are looking for planets around solar type stars, because who cares about pulsar stuff? It's not really quite of interest in general picture, but it's not leading us towards finding Earth-like planets. So it was viewed as a threat rather than as a positive thing, oddly enough. 93, this TOPS report came out, and we had ideas for proposing all sorts of interesting space telescopes. There was a plan to put on an astrometric space telescope that would also bleed off the light from the central star after correcting for its wobble and using it to do radial velocity in space. They also talked about flying a telescope like that on the space station, until they realized Dave Black actually was one of the guys who was going to look into that on the space station. But then they realized space station is the worst possible place to put an astrometric telescope, because the station, if there's an astronaut somewhere on an exercise bicycle, guess what? The whole station wobbles. You did the numbers, guess what? One astronaut on an exercise bicycle, you're not going to see anything of interest. Okay, but also interesting was back then, there wasn't much of a theory for how planets form. The basic working hope was that maybe there 1% of stars have Jupiter-like objects. So it should just give us a feeling for what you'd have to plan on doing in order to find something interesting. Okay, that leads us to our second indirect dictate, which of course is the wobbler. Doppler wobble as a star orbits around its center of mass. So in the case of Jupiter, it makes the sun wobble by plus or minus 13 meters per second. More interestingly, for the Earth, it's about 9 centimeters per second, so about over 100 times smaller. So you have to do some really high precision photometry. But that point, or sorry, spectroscopy. But there were people who knew how to do at least 13 meters per second back then. And the ones who struck pager first were Mayor and Kalo. They were using a 2-meter telescope at Hall Province Observatory, and they had just developed a new Lodi spectrometer for their telescope, which had a nominal error of about 10 meters per second. And they followed a sample of 100 similar type stars that had been left over from a major binary star search that Mayor and Antoine Duquesnoy had just published. And they found a number of binaries, and they found 100 apparent singles. So they thought, well, let's look at the singles and see if they've got something that's not a binary, but maybe has a planet. Well, tragically, Antoine Duquesnoy died. He was a mountaineer, and he was driving back from a weekend in the Alps and crashed his car and perished before this discovery was made. So Michel Mayor picked up Didier Queloz, who was a young person at that point, and added him to the team. And they found this wobble around the star called 51 Peg, one of those 100 stars, which is wobble is now a nice sine curve. So it's essentially a circular orbit, and it's got a 55 meters per second amplitude. There's one data point that doesn't fit very well. I think they may have had too much fresh wine that night, perhaps for observing. But it was spread over a year or so observing. They found the first observing season in '94. They had evidence for a good wobble. They had to wait till '95, September, so '95, August of '95, to take more data points and confirm that it was right. And this wobble is what you would get for a half Jupiter mass object on a circular orbit. Everything sounds fine. The only weird thing about it was the orbital period was not 12 years, it was 4.23 days, which was a bit of a shock. Made it kind of unbelievable because that means it's out in about 10 solar radii. It's going to be a pretty hot object. It'll be a hot Jupiter, as we now call them. I actually was one of the referees on this paper for Nature, and we referees had a lot of issues with this. First of all, because you've never seen a evidence of real detection of a Jupiter-less planet, plus the fact that we figured it's going to be so hot. How can it be there? How come it hasn't been fully evaporated away? So while we sent off our reports to Mayor and Queloz, meanwhile, Michel Mayor couldn't keep quiet about it. So he went to a meeting in Florence, Italy in October and spilled the beans about what he had found. And so at that point, no one's going to bother about our referee report at this point. The word is already out there. And the most important thing was that now the word was out there, other people could run to their telescopes and try to see if it's there. And so Greg Marcy and Paul Butler had their own radial velocity survey going on at the Lick Observatory. And they were able to run to the telescope and just take data continually for 4 nights of 51 Peg. And here's what they found. Yep, 4.23 day period. It's real. So at that point, our referee report was forgotten about and the paper was published as is appropriate. So much for referees. I should also show you that this is a really crappy, scratchy slide because back then their search effort was very poorly funded. So they couldn't afford to make give me a good copy of a slide when I asked. They had no idea who I was, but they sent me a crappy slide, but that's okay. It's like having a Babe Ruth rookie card, I think, in terms of having gone on to find lots of interesting things. So now we had our first, confirmable exoplanet, and at that point, the field, needless to say, really took off. Another indirect method, third indirect method, is transits, which you all know about, of course, from what's happened in intermediate years. And the idea was, let's just trying to find Earth-like planets, and if not Earth, so at least Jupiters. Here's a Northern Virginia astronomer took this for me a while back, and I used it in the talk. This shows Venus, and of course Venus is pretty hard to see in transiting because it's 100 radius of the sun. That means the amount of light that's being dimmed is a part in 10,000. Much easier to find Jupiters. So Jupiters are 10 times larger. That means it's only 1% dimming of light. By the time we'd found 10 hot Jupiters, HD 209458b turned out to be one you could detect the transit in front of the star. It was actually found by a 4-inch telescope in the parking lot in Boulder, Colorado by Tim Brown and Dave Charbonneau. Dave Charbonneau was still a student.
Well, they knew about it ahead of time, all right? They knew when to look.
Well, no. It was hot Jupiter, they didn't know transits.
Yeah.
The radial velocity
Yeah,
model,
yeah.
yes, I'm sorry, yes. And there's another group also that found almost simultaneously. So there were actually 2 separate detections. So it was a real. That also helped buttress the whole field because there are some folks who were worried that the radial velocity detections were spurious. It was due to strange line shapes. David Gray from Western Ontario argued that. But by the time you get velocity wobble plus a second method saying it's real, not just several telescopes saying it, but different methods, then you really know you're onto something solid. So transit photometry became a wonderful thing to start thinking about. And at that point, 2006, I was part of the Kepler team that Bill Baruch had put together. And at that point, we were anticipating launch just about another year or so. So the idea is to fly, get above the Earth's atmosphere, which makes it hard to get that part in 10,000 precision. Part in 100 you can do, no problem, but part in 10,000 you need to go to space. So this plan was put together to put 1.4 meter primary with a 95 centimeter Schmidt corrector lens on the front of it, fly in space and stare at Cygnus constellation, look at a couple 100,000 stars for about 5 years. And the NASA level 1 requirement for success was thou shalt find 50 Earth-like planets. The point was not to just find more Jupiters, but to find Earth-like planets transiting in front of their stars. Of course, Earth being farther out, you got a much smaller chance of having a cult the transit of the stars. So you have to look at hundreds of thousands of stars in order to find hopefully 50 Earths. So that was pretty exciting to be in. So again, in 2006, this is what we're looking forward to launch just the next year. We also were talking about then, because of that various NASA involvement, JPL got heavily involved, and they were planning to do astrometry as well, and to fly an interferometry mission, which this concept was basically a 10-meter boom with two siderostats on either end, just flats, which would then be used for a beam combining unit in the middle to try to do a nulling interferometry between the reference star and a background, presumably nearly fixed star. And the claim was that this would be able to measure the wobble of the target star to about 1 microarc second. In case of the Earth, the wobble induced on the sun-like star is about 2/3 of a microarc second. So it's sort of signal noise of 1. But the claim was we'll just do it over and over again 100 times, same star, and use root n statistics to get down to a 1/10 of a microarc second accuracy, which you could really believe that you found an Earth-like planet. So that plan was to go for Earths. At that point, we thought NASA JPL spent a lot of time developing the pico arc second metrology that was, picometer metrology that was necessary to put SIM together. I spent a lot of time at LA airport flying back to JPL to go to these meetings or reviews that were held like, every couple of months. We go out there and fly out there and review the technology. It was really coming along. We thought it was a potent mission that will fly. Believe it or not, we were also, of course, talking about actually doing direct detection using a chronograph. Here's the perfect chronograph, the moon. Here's the original chronograph. You can see the solar corona. Moon does a great job, but of course the problem is all that diffracted light around the edges. So that's the killer. So in order to actually find an Earth-like planet around a nearby star, the chronograph, you got not only block the light, but deal with that diffracted light around the edges. So again, JPL spent a lot of effort trying to figure out how to do that. John Trauger developed what they call the hybrid Leo chronograph concept, and it was put together into something called the terrestrial planet finder chronograph concept. Again, planned now for launch a little bit longer in 2016, because we knew this was going to be a very major mission. It was not going to be cheap. SIM was relatively cheap in comparison. This would be a multi-billion-dollar mission. And the plan was to fly a 6 meter by 4 meter primary mirror with an off-axis secondary to avoid having any diffraction effects from the secondary in your field of view. And it was that odd shape, elliptical shape, because at that point, the largest launch vehicle we had available was Atlas V with a 4.2 meter fairing. So that your telescope learned up any wider than 4 meters. They weren't thinking about folding things up back then. I should point out now that Falcon 9 has a 5.2 meter fairing and the Starship has a 9 meter fairing. So keep those numbers in mind in the future for future chronographs that may or not be segmented. But we thought we were going to get this to fly, and even more ambitiously, well, let's just go to infrared lengths too and have a TPF interferometer with, in this case, 4 sort of 1.5 meter unit telescopes with a 5th beam combining unit to do the knowing interferometry. And this would not be on a fixed truss like SIM was. These would be movable in space. They would be formation flying, and that means they could change their resistances and fill out what's called the UV plane and actually do imaging at infrared wavelengths. And interestingly, at this point, we were actually working closely with the European Space Agency. We had multiple joint meetings in Europe and here. And the Europeans wanted to go in on this and help build it with us. They had their own concept, which is quite similar. And it was named the Emma Darwin concept because it was sort of like Charles Darwin exploring some new field of science. And they decided it's time to give a lady some credit. So it was named Emma Darwin in honor of Charles Darwin's wife. So at this point, this is 2006. These things were in the future. We even thought we had buy-in from the federal government because in 2004, George W. Bush reading probably the text for the first time, not understanding what he was reading off the teleprompter, said we should build telescopes, look for nearby Earth-like planets. So we thought, oh boy, we were ready to go. Congress actually was planning on doing this. But it turned out to be an unfunded mandate. As you will see. So that's where we were in 2006. Here's Discovery Space. We basically just had radio velocity planets. A lot of them. Lots of hot Jupiters and cold Jupiters, and what were just simply called super Earths down here, because we didn't have really any transits to speak of, very few transits except of Jupiter-like planets. So these objects down here, some of them might now be called sub-Neptunes, but we just call them super Earths because we only knew their mass, not their density. And nothing quite over here by Earth yet, where we're all headed for. So here's conclusions of 2006 talk. Yeah, we got pretty much what we expected. Gas giants, ice giants, presumably super Earths. And the radio velocity folks, Michel Mayor and Butler and his colleague Steve Vogt, they had predicted that based on their radio velocity detections of Earths around M dwarfs, which they could measure, that habitable planets might be there around 10% of stars. So the factor in the Drake equation, eta sub Earth, was roughly 0.1, which is not zero, and that's pretty exciting stuff. And we thought we had Kepler, SIM, TPFC, and TPI coming along, pretty upbeat talk. Okay, that was 2006. Well, what happened? Well, Kepler did fly. Back a couple of years later, 2009, it had a near-death experience. By that point, the cost had risen about $640 million, and actually had what NASA rightly calls a cancellation review, where it was on the line. It could have been killed at that point because it was running late and it cost more than it expected, which is not uncommon in NASA missions, as we all know. But it survived the cancellation review. It flew, ran for 4 years. It studied 170,000 stars. And the key thing is, though, that it had 4 reaction wheels, basically gyroscopes, to study it. And before launch, we knew that those reaction wheels, which are identical as flown on the spacecraft, they were acting flaky, not working well. At that point, given the cancellation review and everything else going on, it was decided just to go ahead and fly it with those same seemingly defective reaction wheels. So after taking data for about 3 years or so, one of the reaction wheels failed. Okay, we really only need 3, and we had a backup, so we flew for 3 reaction wheels for another year, and then after 4 years, another reaction wheel failed. At which point you can no longer have that very high 24 combined differential photometric precision that was the top line Kepler goal. And so at that point, the prime mission ended, but of course Kepler went on to do the K2 mission to look for wobbles of photometric transits around M dwarfs, where it's not so hard to detect because the M dwarf itself is smaller and fainter. So you have better contrast there in terms of photometry. But in terms of the primary mission, it was sort of limited to only 4 years. And 4 years, of course, if you're looking for true Earths with 1 year periods, that means you could have maybe three transits occur. And the more transits occur, the more likely are that you're actually seeing something. So you're sort of limited in what you can find. But one of the first things they did when they took off and opened up was look at a ground-based detection, HAT-PEEP. That's from the Hungarian Automated Telescope Network. And they demonstrated the precision. So you can see the eclipse, a nice 1% eclipse transit in front. And then as well, when we get this over here is the blow up of the eclipse of the planet going behind. So this is down to about 100 parts per million transit photometry precision, which is what you need. So we knew Kepler could do the job, but part of the problem was that the stars, like this one, turned out to be pretty noisy. We were using the sun as our assumed example of a typical star in the solar neighborhood. Turns out the sun's pretty quiet compared to most stars. And so that made Kepler's job even harder. As a result, as in 2017, when basically all the Kepler prime mission data has been analyzed, here is what was found. There's really only one confirmable Earth-like planet. Around here shows you the stellar temperature. And so here's sun-like stars up around here. We were hoping to see a whole lot of blue dots up here. Down here, the M dwarfs, so you can see a lot more interesting super Earths. But they did not find the 50 that was the level 1 requirement that was declaring success. But the thing that they could do, of course, was make estimates of what is actually there that just can't be seen yet. And so the last estimate that's been published by Steve Bryson, who's led this for the Kepler team, is the ATIS of Earth is about 0.6 to 0.8, which is pretty healthy. It's even more than what the radio velocity folks have claimed. Because of course, transit photometry is they have many more objects detected by them than radio velocity. They have pretty good statistics from that point of view, just not too many detections. So that was on the whole, I think, even though it did not meet the level 1 requirement, we view this Kepler as a very successful mission, needless to say. However, around that time also the decadal survey came out, 2010. There was one panel called Electromagnetic Observations from Space that I sat on, and there of the 16 people on the panel, so 4 of us were some exoplanets, the others were kind of more extragalactic folks. And guess what? When you take a vote, you don't necessarily win. We knew back then that things were, money was tight, and so the sim I think came in second. At that point, it was thought to be maybe only needed another million or so. I'm sorry, another billion or so to fly. And they'd already spent 600 million developing at JPL. And the 2 TPFs were basically so much farther down. I don't think they even got voted on. But what won was the W first mission. So play on the word of trying to beat the Europeans to measuring the cosmological parameter W first. But it's the Wide Field Infrared Survey Telescope. And they did, they did this by combining 2 mission concepts that we presented to the panel, one for dark energy survey and the other one by microlensing from Dave Bennett, who's here in Goddard these days. So microlensing was what was offered to the exoplanet community, although at that point there were very few people who were worried about microlensing. So those of us who were in the community were looking for Earth-like planets. It's like being handed a pulsar planet. What do we do with this? But we've learned to accept it. Let's put it that way. Of course, W first has become the Nancy Grace Roman Space Telescope due to, in part, to having these 2.4 meter optics left over from the failed NRO program. NRO, their program was building several of these telescopes, and they were went over cost and over schedule, and so they just decided to hand them over to NASA at one point. We had a meeting at Princeton that Dave Spurl chaired to see what we could do with them and would they be useful for a W first. And it seemed like what a deal. We've got this mission concept, and here we have a free space telescope. We can, it won't cost us hardly anything to build it, right? Well, it turned out not to be the case. But that's what helped motivate W first getting a sort of a head start on being coming into action. NRO, I think, has also decided since then that instead of flying a few very big telescopes that can be hit by an anti-satellite weapon, to send up lots of smaller guys in case of a wartime situation, so you don't lose your eye just by 1 or 2 hits. So it changed their philosophy altogether. So Nancy Grace Roman Space Telescope, as I said, Nancy Roman, who was a student at Swarthmore, she was a student of Peter Vandekerk was her advisor. So I'm pretty sure she must have measured some place, though I never had a chance to ask her about that. But Nancy Grace Roman was actually a good friend of my colleague Vera Rubin at Carnegie. In fact, Chris Stark, I think you may remember, Nancy Grace Roman would come to our seminar. She lived close by. I think she's the lady who's given the credit for building Hubble. She lived in the neighborhood, friend of hers. She'd come to our seminars, and we'd get these young kids sitting here giving great talks. And Nancy, with this gray-haired lady, was sitting in the back. She liked to knit, obviously, in the seminars. And people would see this gray-haired lady sitting in the back. And then at the end of the talk, she asked an absolute precise, concise question that blew them out of the water. It make them wonder if they knew anything at all about astronomy, but she was really sharp as a tack. So I think it's perfect to have this named after her, especially since it's all, again, Hubble optics. It's kind of, I mean, Hubble in both ways. I was at a meeting at Caltech last summer for what the Roman Space Telescope would do, and it was interesting to hear people talking about what Roman will do with Rubin. Because they're talking about what the Roman Space Telescope will do allied with the Vera Rubin Observatory, the LSST in Chile. These people had no idea when they're saying Rubin will work with Roman, Roman will work with Rubin. They didn't know that Rubin and Robin were actually good friends. And so they just thought that was fantastic. That long after these 2 grand ladies have passed from the scene, their names will be used interchangeably in the future by doing science together. Okay, so we're only a little over a year or so away from launch. Hopefully that goes on schedule. And looking for exciting science to come out of Roman, particularly about microlensing. So back to microlensing. This is something Einstein had predicted back in 1936 or so. He thought it would never happen, but someone egged him on about it. He finally published a paper about it. The idea is, of course, that nearby you look at a bright background star and wait for it to miraculously start brightening over a period of about a month or so. And if in addition, the nearby star happens to have a planet around, you'll see a secondary brightening over just lasting over a period of a few hours to a day or so, indicating there's a planet there as well. So that's a pretty exciting way to indirectly find, fourth way of indirectly finding evidence for planets. And so what we'll let me first do, here's a graphic from a paper by Matthew Penny and Scott Gowdy and others, showing you the discovery space again in terms of blue, what micro lensing should be able to detect. And the red, black are the radial velocity ones, and the blue points are actually not real detected planets. They're just a sampling of some theoretical prediction of what might be out there. And blue lines show you where the micro lensing has the very nice complementary detection bias in terms of compared to transit photometry. So they will be able to find Earths sort of just barely. But probably not too many of them. They hope to find maybe 1,000 planets altogether. But even if they do find a few Earths, it'll be spectacular, but there'll be no follow-up because the microlensing event is a one-time event. And you don't even necessarily know what the foreground star was. So they're often K or M dwarfs, but it's totally unsatisfying. We want more. We want to be able to know exactly what the star was like. It's part of, in order, you have to really know the star well in order to understand what the planet is around it, because you have to disentangle the planet system from the stars. All right, what else have we gotten since then? Well, here's a gift. George Ricker came up with a test mission. This came for only mere $200 million, a mid-X mission. It was basically pitched by George Ricker as a planet finder for James Webb Space Telescope, because they knew Webb would do a great job for transit photometry, all of its near-infrared, mid-infrared, high precision spectrometry. Will do fantastic characterization of the atmospheres of transiting planets. So TESS was launched more or less on time. I think it's found close to 500 confirmed planets by now. It's a relatively small scale. Those are four 10.5 centimeters telescopes. It does an all-sky survey. And it's on this weird orbit synced with the moon. It's a 14-day orbital period, and it means it turns out it only spends 28 days per sector of sky that goes to another sector. So if you're looking for only 28 days of data, it means you want to see at least 3 transits. It means the orbital periods have to be less than 10 days or so. And that means if you're looking for habitable zone planets, they better be looking around M dwarfs, because those are the only ones where the orbital periods are short enough that you'll be in the regime where you can have liquid water. So basically TESS is going out there searching every M dwarf it can find for habitable worlds in order to be passed on to James Webb Space Telescope to see if we can see an atmosphere in them. So, and of course, the other big thing which has happened since then is Webb did launch successfully December 2021 and works really well. We all know that. And it's great for doing transiting planets. Would have been nice if we could do coronography too, but of course, with that segmented primary, that makes it difficult compared to a unsegmented primary. It also has a secondary, which is on axis with struts as well. It's actually kind of like what W first is. It's not ideal for coronography, but it does make it harder to be able to try to take out diffraction and scattered light from the segments and the struts in the secondary. But for transiting, it's wonderful and true. Nice big 6.5 meter aperture, lots of signal there. So the point was that JWST would look at the test planets, but we got another gift from another ground-based transit system. The Belgian system, the TRAPPIST system, was found. This is a star about 1/12 the mass of the sun. And amazingly enough, it has 7 planets all lined up in a flat plane oriented towards us so that we can see all 7 detections, transits, and with transit timing variation, get an estimate of what their masses are. And so here's an incredible gift from Mother Nature to give us 4 habitable zone planets, all ready to go for transit photometry. You know their masses roughly? Do any of them have atmospheres that can be detected? So by the time I gave this talk on campus, and the day before, so this showed up in the Washington Post, for what do you want to look for in an atmosphere? Well, you look for methane, CO2, water vapor, organic compounds, oxygen, ozone, and Amazon packages, which I thought was appropriate because Jeff Bezos, I wonder if he read the paper that day or not, but And of course, the key thing is if you have both methane and oxygen or ozone, that pretty much means you have to have active biological sources of both. Abiotic compounds, processes don't tend to produce that much of either. And if you have methane and oxygen, they will react with each other and you will end up with doing chemistry that removes either the methane or the oxygen. So if you see both of them, it means you probably have some methanogenic bacteria. And if you have oxygen, you probably have photosynthesis going on, which we take as, I mean, it may not be intelligent life forms that have Amazon packages, but we will be happy to find some little creatures that are methanogenic or doing photosynthesis. So there we are. And then, of course, what has JW found? Well, here was there may have been some more spectacular discoveries since I gave this talk, but here's a super Earth. It's probably not a it's kind of maybe what we call a sub-Neptune because it's has 8 times the Earth's volume, but only 3 times the Earth's mass. So it's probably a little bit puffy or watery. But they do have water in the atmosphere, which is fantastic. The only problem is it's steam. So it's still not quite the kind of place you want to buy real estate, but it's a step in the right direction. And someone in the room can correct me, but as far as I know, and all the talks I've been hearing, we've yet spending a lot of JWST time. All we got for this bare rocks from TRAPPIST planets. Anyone bring me up to date on that, please? I'd love to see that we found detection, but maybe, we'll get up there. A lot of other test planets, maybe we'll find something eventually, but right now we still don't quite know what these things are besides bare rocks. Okay, what else has happened since then? Well, another decadal survey. And this time I was not on the panel, and so they decided, well, let's fly TPM, basically. We'll show Alan Boss. So yeah, they said, let's at least chronographing. You shall look at 100 planets, and you shall find 25. Because they decided 8 of them are 0.25 to 2 significant figures, and so there we go. We finally have in decadal survey the top rank. In the past, there have been lower ranked planet finders, but here you have top rank, and we all know these days top rank is at best one that's going to make it through if you even get that out. So that's fantastic progress from the point of view of the decadal survey stuff. But in order to fly that thing and build that chronograph, you better know what you're doing because it's an unprecedented leap forward. And one of the nice things about the Roman Space Telescope is they just, besides doing the dark energy survey, microlensing survey, they decided to put on a tech demo, which is a purposely built chronograph to see if we can really get this to work. And here's actually the chronograph sitting out in the assembly bay out of JPL as of last year. I actually had the honor of chairing the independent review team that oversaw the building and manufacturing and testing of the chronograph for the last 5 years, and it's ready to go. So this will be our first purposely built chronograph for space. There are a lot of chronographs up in space and they're built specifically for planets. This one is built. So here's a somewhat complicated discovery space plot showing you the vertical axis, the contrast you need, and the lower left is where we want to go with 10 to the minus 10th contrast for Earth at 10 part distance. You have to be a separation of only 1 arc second, so very close to the star. And you can see the lines up in the upper right are what can be done right now with HST or JWST Mirlock, HST STIS, and ground-based 8-meter telescopes, the Gemini GPI or the VLT Sphere. They're up at around maybe 10 to the minus 7, 10 to the minus 6 contrast at best. And we're hoping to get with Roman chronograph, we actually hope to get down here, this bottom area, the blue and the red lines. But the so-called level of requirement was originally about a little bit over 10 to the minus 8. In order to make sure we get the level of requirement right, they backed off on that and said the new baseline is basically 10 to the minus 10th. See, they can't quite lose the cursor here. Oops. So if it achieves a contrast of 10 to the minus 7th on a few bright stars, it'll be declared victory, saying we know how to make the chronograph. But of course, this thing has been built for the last 5 years and tested to go down to the 10 to the minus 9 level. So I, for one, will be really surprised if we don't actually get to 10 to the minus 9 because all the bits and pieces are there. We don't have all the variations of the chronograph that can be put in. There's a shaped pupil and Leo hybrid Leo, and there are a few other options that were neglected. But it should perform really well, so it should come within maybe a factor of 10 or so of where we want habitable worlds to go. So that's pretty exciting. We think it's gonna be a success. So meanwhile, habitable worlds, people in this room probably know a lot more about this than I do, that's for sure. We hope you'll be able to take an image like that one that's shown on the left. Earth will be kind of barely visible there, along with Venus and Jupiter and Saturn. And of course, the big question is, it's launching maybe 20 years from now, assuming we can keep the NASA budget. Something that the new budget office doesn't do something to it. And the notional architecture, I believe, given that Goddard is running the show, has a certain fondness for segmented hexagonal mirrors for some odd reason that they fold up into space. And so they're talking about one notional architecture with this, be this. I know folks are right now actively trying to figure out controlling refraction from a segmented mirror. I'm also chair of the Exoplanet Exploration Program's Technology Assessment Committee, and Remy Sumer and his folks up at Space Telescope are trying to figure out how to build a chronograph that will work really well with a segmented primary. So folks are working on that. Hopefully they'll be successful, so that we have options of either a monolithic primary that happens to fit inside Starship, or segmented foldable, I'll have James Webb, one that we can afford. But that's all work that's happening right now. So what else happened in 2020 is, well, of course, ground-based stuff is important too. So there have been for many years the Caltech 30-meter telescope project, and it's been in competition with Carnegie's Giant Magellan Telescope. And they're both TMT on the left and GMT on the right. Both of them have lots of money invested already. We've got university colleagues, international colleagues, many nations across the world are involved in putting some money in, but they're both short on money. Be nice somehow if they can combine and just, build one together, but so far they've been unwilling to do that. The estimate is they basically need about 1.6 billion of NSF money. That, of course, is now an estimate from 5 years ago. And the last thing we heard is that NSF's budget is threatened just as much as NASA's may be. They're talking about having NSF's budget from 9 to 4 billion, in which case you can believe there's not going to be any money for this project, which already would, even at the current NSF budget, trying to get this money out of their major research implementation stuff would have been very difficult. But needless to say, these two major ground-based telescopes are continuing to hope that they will survive and be built. Here's an artist's rendition of what the GMT might look like. This nice big boxy dome with open vents, because the key thing for a big dome, they realize, is you do not want to interfere with the temperature of the night sky. You want your telescope to be the same temperature as the night sky and to cool down quickly, because otherwise you have something called dome seeing, which makes it even worse. It's worse than the atmosphere above you. So that's the kind of preferred design, at least for the GMT. I'm not quite sure why TMT is designed the way it is, but that's how GMT intends to come down to the night sky temperature. And GMT is actually, if you look on their webpage, why are they wanting to build this? Well, here's the first thing that pops up is, look for Earth-like planets. I often think of the Carnegie observatories as being mostly extragalactic folks who couldn't care less about planets. Somehow they too have not a religion, and they decided we want to sell this GMT. We better find some Earth-like planets. Well, how are you going to do that? Well, it turns out, back to the Alpha Cen system, Proxen B. Alpha Cen is a binary separation about it's 80-year period. 17 AU. Beta Cen is another binary, and Proxen, you can't really see it. It's inside that red dot. It's a red dwarf, 1/8 the mass of the sun, and it turns out to have a radial velocity planet, which is actually found by one of our DTM postdocs. He may have overlapped with you, of course. Again, Guillermo got us back to Spain and Barcelona, and launched a big project to use one of the European Southern telescopes to basically look at Proxen all night long for a year or two at a time, pick up that very faint lava. So here is one, and it has, turns out to be 1.3 Earth masses, limited orbital period, close by. It's a perfect thing to look for. And it turns out GMT could do it. Here's, again, a contrast type plot. Sort of can't quite read it with all those other dots, but Proxen B is up somewhere around 10⁻10th contrast in reflected light. And it's it's close, pretty close to a star, but at certain parts of its orbit, it'll be far enough out that the GMT with its almost a little over 25-meter aperture will be able to resolve it. W first is 2.4 meters aperture, it just doesn't have enough lambda over D to see it, so W first can't do it. But GMT could very well look at Proxen, and of course, we really want to get down to the lower left where the X says. So that looks very promising. That's probably the best, to my mind, one of the most convincing cases for building GMT. Of course, the problem is, Proxen is also in the south, so TMT can't see it. But there's this thing called the European Extremely Large Telescope down there, which is farther ahead than the GMT is. So it very well be the Europeans will grab this one before we can get to it. So how would GMT do it? They're planning on developing a new version of the current Magellan telescopes for 6.5 meter, have an adaptive optics program, which has been running for many years. Jared Males, they're close at Arizona, built that, and they're going to do a giant Magellan version of it for the GMT. And here's what they think they can see in terms of the size of the radius of the planet and how far where they are, and a big darkish red dot at the bottom, Proxen B. That is one of the top things on their list. These are known planets, so they know they're out there. They're known for radio velocity, but these are the ones that the GMT can go and try and look for evidence for atmospheric signatures in there through direct imaging. So that would be an advance for direct imaging from the ground, doing the best they can with adaptive optics. And they're also planning on building as a first line instrument, a really high precision spectrometer. It's one of the first of the so-called extreme precision radio velocity spectrometers. Right now, the best people can do is they've advanced quite a bit from Mayor's 10 meters per second. The high precision velocity now is roughly 1 meter per second. And they're hoping to get up to 10 centimeters per second, which is sort of right on the edge of what Earth's wobble is, which is 8 centimeters, or 8 or 9 centimeters per second. So that's the plan, is to, besides looking for Earth-like planets by Magellan AO, we're also looking for their wobbles. And I think through some clever instrumentation, you actually can get some spectral information from not just the wobble, but you can also get the spectral information about the spectrum of the planet through this as well, which would be really clever to do. Okay, here's what mountaintop's been cleared on Las Campanas, the Carnegie Observatory in Chile. Last time I was there, we used to stop at noon and look over towards Magellan, because that's when they fire off the explosives to clear the rock off the top. So we look over and see this big puff of smoke off the top of Las Campanas. So they go in and look. I'd like to say that this has all been built, but it hasn't. The mountain's been cleared. The auxiliary buildings are there, but that big cutaway building in the top has been designed. There is a contractor who is beginning to develop it, but it's not been built yet. So we still need just another 500 million, maybe $1 billion tops. We'll glad and ready for you. Maybe unfortunately, like I said, the LT may beat us to it, so I'm not sure how that would work out. So, all right, conclusions, part one. Here's Discovery Space again, up to date. All the test planets, Kepler planets, radio velocity planets, a few direct imaging planets, a few microlensing. Nothing quite there around by Earth and Venus. Nothing much there. That's really what we want to fill this in. And of course, we're going to have to leave that to Admiral Wells Observatory, I guess, to fill that in. But there are, of course, a number of super Earths and sub-Neptunes and things that are interesting. And looking at some of those, of course, we do have, here is Prox B in yellow. There are a couple of other planets possibly around Proxen. There's a C, which was not even thought to be real enough to be put on this plot, and D, which is some people argue about, but B is pretty definite, it's definitely there. And these are all good candidates for being able to characterize their atmospheres. And I'd like to close it with this, because you also listen in red, there's Barnard B. So good old Peter Van Eyck, he actually died right around the time that 51 Peg B was discovered. He didn't quite live to see the first extrasolar Jupiter found. But if he listening to us in heaven right now, Peter, you are right. Barnard star has at least one planet, and it's even sort of Earth size. So how about that?
I think it might have just been us that there's a C, D, and E.
My God. So there you go.
Like today.
Yeah, fantastic. I will change those slides when I get back. Thank you for that, Chris. Yeah, so Peter, did you hear that, Peter? Yeah, okay, good, yeah. All right, so there we are. We made a tremendous amount of progress. We've got fantastic instruments functioning already, tests and JWST. Lots of plans for the future habitable worlds. And at some point, I hope to actually be motivated to write a fourth book in the series, covering the next up to say 2028 or 2029. We won't have habitable worlds built yet, but not sure if I'll last till 2045. I'm getting kind of old myself, but you never know. There could be a fifth book. You'll certainly be around to read it if I make it. That's where we are. I'd be happy to take any questions, people.
Excellent talk, Alan. So yeah, we have time for just a couple of questions. I definitely want to get some from online in the room. So Carl, I'm going to go to you first if you want to unmute.
Yeah, hi, Alan. Thanks for the really nice historical overview. I just wanted to add a couple details to that. There was quite a time turning around TPF from an interferometer originally to a coronagraph. Astro 2000 thought they were approving a TPF interferometer when they endorsed it for detailed development. It took us like 4 years through lab experiments to turn it into an optical coronagraph that HWO now is. So I wanted to add that to the story. And then also I wanted to mention that in 2007, the NASA administrator, largely because JWST was overrunning, basically put pause on SIM and TPF-C and I, leading up to you guys finally killing all of them in Astro 2010. So I wanted to mention that too. Thanks.
Yeah, thanks, Carl. Yeah, there are lots of details I skipped over. That's why you need to buy those books and read them. There's a lot more gory details in there. Yeah, all the laundry is there. Nothing's been washed.
Yeah, go for it.
I have a question. So, Oscar, provocative question since you're in the room,
Sure.
which is, what's your take on, the pulsar planet not being, valued at the same level as 51 Peg B? Right, we've awarded 51 Peg B with the Nobel Prize, and the first exoplanet somehow did not get that. So,
Yeah.
What's your?
Wolfson's gotten some credit. He's gotten some credibility for it. I mean, he deserves having found the first Earth mass planet. It was more a question of competition with to do pulsar planets. You need a Arecibo, and we want to build something neat like SIM or TPFs and do coronagraphy. Not just get a weird wobble, and what more can you do to characterize the system? Plus, this is presumably it's like the Black Widow pulsar. There are these weird objects left over in pulsars which have gone through, blown off their outer layers and incinerated what's in orbit around them. So their interest from the point of view of astronomy is just what is out there. But it's probably the pulsar planet is a burned out cinder. So we're looking in the end for Earth's life with life. I mean, that goal has been driving the field ever since the beginning. We start out looking for hot Jupiters and you can find them, but we're looking for lifelike planets. So it's just a question of, we didn't want them to steal our thunder in some sense, because this is back when Charles Alachi was the head of UPL. He would come and give us pep talks and say, yes, go, we should start a new program at NASA and do it. And then along comes pulsar planets. Who ordered that? And so it's and there have been a few more found since then, but I think there will be 6 or so altogether. They're interesting. They're taking anything away from them, but to my mind, they're just not as interesting as trying to find Earth-like planets. It's a personal choice. Some people think fast radio bursts are the all and all of the universe, but that's not where my interests lie. But we were being a little unfair, but that's okay. I just wish it would have given us more of a boost. If thinking it as a boost, that would have been wonderful, but we thought it more of as a diversion.
So we are at the time, but are you okay to stay for just a couple more minutes? I have
Sure.
questions. So I think RK was next. RK, do you want to unmute and ask your question?
Yes, I enjoyed your talk, and I had a question about the Gaia mission. My understanding is that Gaia has been able to achieve astrometry at the level of milliarseconds. So I was wondering if that's been applied to looking for stellar wobble from exoplanets.
Yes, we're expecting when the Gaia, whatever final data release comes out in a few years, that they're going to find probably hundreds, if not thousands, of Jupiter mass planets, evidence for them, combined with other radial velocity follow-up. There are several groups that are working very hard with the existing Gaia data, as well as ground-based radial velocity and imaging to to nail planets that way. So Gaia is going to be a major step forward, but it's not going to bring us down to Earth. It's basically just Jupiters, which are interesting in their own right, especially if you get these will be longer period Jupiters, or not hot Jupiters, because the astrometry prefers a longer orbital period. So if you find a bunch of cold or medium warm Jupiters out there with room for inner finding an outer Jupiter used to be thought of as a sign for finding an Earth. We may not be able to find the Earth structure. If we can find the Earth, find Jupiters, that may tell us where to look for the Earths. So Gaia will make a big step forward in that direction.
Cheers. Just to follow up on
Yeah.
quick. Yes, I think I have an hypothesis on why we found the pulsar planets. It's actually related to history of discoveries in astronomy. We'll talk about it. I'm trying to write an article on it, but go ahead.
Well, I think
Thanks for a nice review. So I just want to add to the, your story of explanatory discovery, as I know what you might be mentioned, I came a little bit late today. The another aspect is to characterization using the space physics methods, to characterization of atmospheric to make sure that those planets like Proxima B has an atmosphere, from what we learned from our Earth. The point is that it's around 5 billion year old system, right? So and it may already lost magnetic field, and the atmospheric could have eroded the atmosphere. So we probably along with those technological innovations, we need probably to also, it would be nice to have a flux light to talk about the space physics, how space physics contribute to that, especially helium physics contributes to this topic.
Yeah, I did not even mention that, but of course, M dwarfs are dangerous places for life because they're fully convective and they're flaring and doing horrible things like that. So that is something to worry about. You may have a seemingly habitable planet that gets zapped by flares that may not allow very advanced life to flow. Maybe microbial life might be perfectly fine, but yeah, that's definitely a whole nother talk. It's space physics interactions with the star. So it's again back to know your star, know your planet. Just stars more than just a source of gravity. It's light,
Right.
It can also be gamma rays.
awesome. Well, I think we will stop it there. Just for sake of time, I think we're stopped there, but I think Alan's around if you want to meet with him for lunch or meet with him after. But I'm going to end the meeting. So thanks for everyone who joined online and was able to join the room. Let's thank Alan again for the great talk.
So if anyone is interested to join us for lunch here at the cafeteria, let me know, and then we'll go together.
I was just gonna